All right, this is what I want to show you. If you go, let me fix the microphone real quick. Move it away. Sorry about the noise. If you go to modules and go to ebook, it's going to open this. You're going to click here. It's going to open the ebook for you. I cannot do that right now. Let me see if it's going to work. Oh, yeah, it works fine. And then you go to chapter 2, which is where we are, section 2.7. Let's get there. I really want to show you how to get there as well. So we go 2.7, tangents. And as you scroll down, you're going to get to this explore it. So this is cool. So let me zoom, or let me maximize this so you can see how cool this is. If you go to explore and test, here's the equation that we just did the math for, f of x equals x squared. And you can choose a different point if you want by moving this slider. And this green square that's moving around our point is this magnification here. So you can also choose how close you want to look at it. Do you see? You see a piece of the black graph, which is the function, and a piece of the red graph, which is the tangent line. As you move and you zoom closer, there's almost no difference between your line and your graph of the parabola. Okay? And you can even choose a different function, such as this one. Right? You can see as you move, the tangent lines move together. Okay? And the same thing happens though. As you zoom in, there's almost no difference between the line and the graph. Try another one so you can see. Cosine, right? Cosine, you're going to see that there will be points like this one where the tangent line will be horizontal, right? But then as you move, the tangent line changes and the green square, sort of visualization square, follows it along. But even here, right, it doesn't matter. If you zoom in close enough, there's almost no difference between the red line and the graph. The tangent line and the graph. You can zoom in closer. You could zoom in closer. This applet here doesn't let you. Only 50 times magnification. If you were able to do 100, 200, you'd see that's even closer. The red and the black line. The red tangent line and the black. And you can move this while it's magnified too if you want, right? So you can see here it's a little farther away, but that's because we can't get even any closer. Take a look at this, look at the concepts, look at the example, and look at when you'd use this. This is a very important concept and idea. It's very, very, very important. Take a look at this, and I really just wanted to show you this before, we move on. So let's go back to our slideshow. Okay, so let's talk about velocities a little bit and see how we can use this idea, this very powerful idea of derivative. Or so far only the tangent line, right? I'll talk about derivatives soon. So in general, when you have an object whose position is given by s equals f of t, s is the displacement, right? The distance between a point and another. So from the origin and the point that it's currently at. We call this the position function, right? And on a time interval between a and t plus, or a plus h, the change in position is a plus h, f of a plus h minus f of a, right? You start with a seconds, and you go to a plus h seconds. Then f of a plus h is the position at the end of the interval, and f of a is the position at the beginning of the interval. The difference is the displacement, right? So they're basically exemplifying what I just said, right? So this here is the difference. That is going to be, for us, the average velocity is going to be the displacement divided by the time. So it's going to be f of a minus f of h minus f of a plus h minus f of a divided by h. Note, not coincidentally, That's the expression of the secant line that we used before. And we're going to use this idea to find so this is the average velocity in the time interval h. What we do then is we make the time interval smaller and smaller to find the instantaneous velocity. Okay? Same idea. So that's the instantaneous velocity. Okay? Very, very important to remember. We're also using the same limit that I've already been referring to as the derivative, but we're going to define that precisely later. Here's the example. Example we talked about before. I kind of changed the CN tower to the Space Needle, but that's the idea, same idea. You have 450 meters above the ground. It could have been feet, whatever. What's the velocity of the ball after 5 seconds? So again, we want an instantaneous velocity. I think I'll need to do some math here. So the instantaneous velocity, first I need, remember Galileo, right? S of t equals 4.9 t squared. Just double check to see if I'm not making a mistake, but I'm pretty sure that's correct. So that's something that was given to us. And we now want to know the velocity, but I don't want to fix time equals 5. I could do this. I could do v of 5 equals to the limit as t approaches 5, or as h goes to 0 if I wanted, of s of 5 plus h minus s of 5 over h. I could do that. That would answer the question, right? So I'll do that once just to show you how that works. So let's see. So that's going to be the limit h goes to 0, 4.9 times 5 plus h squared minus 4.9 5 squared divided by h. So now algebra here and a lot of manipulation. 4.9 times 25 plus 2 times 5 times h plus h squared minus 4.9 times 25. All that divided by h. Use distributive property here, so I'll get 4.9 times 25, and you're going to see soon why I didn't bother doing it. So that's 2 times 5 times 4.9. 2 times 5 is 10 times 4.9, that's 49h plus 4.9h squared minus this guy, so 4.9 times 25. And here's the reason why I didn't bother multiplying, because I knew it was going to cancel out. And then divided by h. I think I'll add a page to this just to see. So then you have 49h plus 4.9h squared, all that divided by h. Factor out an h from the top. 49, so h times 49 plus 4.9h divided by h. These two cancel. And now you can plug in h, right? Because now there's no longer any issues with the denominator being 0. So that just becomes 49 plus 0, which is 49 meters per second. So that's Galileo there. Okay. That's the derivative, or the velocity, instantaneous velocity after 5 seconds of fall. Instantaneously, right, after 5 seconds. After 5 seconds, you're not looking at the average velocity anymore. You're looking at the velocity at that instant of time, at the precise instant of time, 49 meters per second. Okay. Okay. So how fast? So this is one way to answer the question. The other way to answer the question, and I'll do it in green so that you know it's a different solution, and this is something that I hinted towards before, is I'll look at, rather than look at how I started this math again, right? Go back. This was 5 plus h and 5. Rather than writing 5, I'll write t, and then I'll get an expression for v. So v of t will be the limit h approaches 0. Same thing, but instead of having 5, I'll have t. And then I'll plug in 5 at the end. So it's going to be the exact same math, except now we're doing things with t rather than 5. I'll do a little bit faster, but try and follow along. So it's going to be 4.9 times t plus h plus, sorry, this is not supposed to be a plus, right? It's supposed to be a minus right here. 4.9 t squared divided by h. So that will be the limit. H goes to 0. It's a lot of writing, I know, but you got to write the limit. T squared plus 2th plus h squared minus 4.9 t squared, all that divided by h. I'll need another page for that. So distributive property plus 2th, not 2, right? 4.9 times 2, so 9.8 th plus h squared. Sorry again. 4.9 th squared minus 4.9 t squared. So it's a little bit more complicated because I don't have a 5 to replace as t. So things stay not looking so nice. Add one more page, and then I'll get limit h goes to 0, 9.8 th plus 4.9 h squared over h. Factor out an h. Very last limit I'll ever write in this example. As h goes to 0, this becomes 0, so this is just 9.8 t meters per second. Okay? There you go. Now, because they asked for 5, I can just so this is v of t. V of 5 is 9.8 times 5, which is 49. So that's a different way. You find v as a function of t first, and then you plug in as necessary. What's the advantage of this? Because the math is a little bit more complicated. You can go ahead and follow along the green if you need. But the advantage is that, if you look at B, right, if you go back, how fast is the ball traveling when it hits the ground? How fast is it traveling when it hits the ground? Now they're asking for the velocity again, but at a different instant of time. So I now have v, so that was my answer, as a function of t. I can just plug in any t that I want, and that helps me solve b. As soon as I find how much time has elapsed between when the ball starts falling and when it hits the ground, then I now know exactly what to plug into v to find that out. I don't have to do any more limits. I only do once. And that's what you have there. This is the answer for A. And for B, they use the equation S of t equal to 4.9 equals t squared equals 45. Solve for 450, excuse me. Solve for t by finding t equals 9.6 seconds and plug that into the equation I gave you, 4.8 times t, right, to figure everything out. Okay? Approximately 94 meters per second. That's it. That's the idea. We've now solved the tangent and the velocity problems. I'll talk about derivatives now, but please go back and review what we just did, because that's really remarkable, historically very relevant in math. But okay, let's go on. Whenever you see the same type of limit on finding the slope of a line or the velocity problem, you can see that this shows up multiple times. This is the most important limit we're going to calculate the entire course. We give it a special name because this shows up at every different type of situation when you try and look at instantaneous rate of change. You call the derivative of a function at a. Okay, the derivative of a function at a, and this is f prime of a. So this little line we say f prime of a. Okay, so f prime of a we say f prime of a. That's how we say this, and it's always this limit of f of h plus a minus f of a divided by h as h approaches 0. So that's the derivative of f at a. Okay? Just a given name for this limit that shows up all the time. Here's the example. I'll do this one. Find the derivative of the function f of x equals x squared plus minus x plus 8 at the number a plus 9, sorry. X squared minus hx minus 8x plus 9 at number a. I'm not doing very well today, so it's a good idea if you want to double check my math. But we're at the number a now, so they did not give us a specific value. So from the definition we have f prime of a equal to the limit as h goes to 0 of f of a plus h minus f of f of a divided by h. So we're going to do that. Let me see if I have more pages already. So this will be limit h goes to 0. I plug in a plus h in this expression, so it's a plus h squared minus a times a plus h plus 9 minus, now plug in a into this. Be careful that this minus sign right here has got to apply to the entire f. By adding minus in a parentheses. So be careful with that, okay? And all that divided by h. So now a lot of manipulation and a lot of algebraic manipulation. So this is a squared plus 2ah plus h squared. That's the first term right there. Now minus 8a minus 8h plus 9 minus x squared plus 8x minus 9, all that divided by h. And now we can start canceling things out. Sorry, let me go back because I messed up, right? This was f of a. So this entire thing has got to be plugging in a into where x was. So this is, let me do it in red so you see this is a. Sorry about that. Because I have to plug in a where x was. Okay, I think it's correct now. Just double check. Yeah, looks okay to me. The reason why I messed it up is because to me it doesn't make sense to use a anyway. I just use x plus h minus f of x, and then I replace it with a if necessary, but this is how the slideshow is doing it. The book is doing it, so we're going to do it like this for a while at least. Eventually, I'll go back to what's more familiar to me, and you're going to get used to it as well. But anyway, this is how you do this, how far you go with a, and then you cancel what can be canceled, right? A squared minus a squared. You have minus 8a and a plus 8a. You have a plus 9 and a minus 9. This is going to happen most of the time. A bunch of things is going to cancel out, hopefully. And luckily, because at the end, you want to be able to pull out an h at the top. Right? H. Is there anything else left? I don't think so. As soon as you're able to pull out that h, so pull out that h, you gotta see what's left, because when you cancel out, and a page. So when you cancel these out, you get 2a plus h minus 8. As h goes to 0, that goes to 0 as well, so only 2a minus 8 is left. So that is the derivative of f of x at the point a, at the number a. Okay? We did it. Look back again. Look at the mistake that I made. Make sure you don't make that mistake as well. And there is the, I guess, closer to the conclusion of this part. The slope of the tangent line is the derivative at x equals a. Okay? That's the, I guess, this is the takeaway. The slope of the tangent line is the derivative at x equals a. And you can then write this as your equation, I guess, point slope equation of your line, y minus f of a. F prime a is m and x minus a. Okay? So that's it. We can conclude this by talking about rates of change. The idea is pretty much the same. Have f of x2 minus f of x1 is change in y, right? Delta y is how we're going to say sometimes, or change in y, or variation in y. And change in x is going to be x2 minus x1. When you divide these two, that's going to be the slope of the secant line again, right? The average rate of change. It's important to remember this. This is going to be the average rate of change of y with respect to x. In this interval, it's also important to remember that the interval matters. And as you make the interval smaller and smaller, meaning x2 closer and closer to x1, or the change in x go to 0, right, then that becomes the derivative again, the instantaneous rate of change. Okay? It's again the derivative at x1 or x2, depending on how you look at it, but most of the time x1. And we know that it means that it has the slope of the tangent line as its interpretation, but here we also have the second interpretation, which is to say that f prime of a is the instantaneous rate of change with respect to x when x equals a. That's to say, if x changes just by a little bit, right, f prime of a is how fast f of x is changing. Okay? And there you go. You have two different rates of change. So looking at this, if you zoom in, right, this is a very steep tangent line. So the rate of change is very small, sorry, very large, because very steep, high slope. Then f is changing very fast near p, whereas here the slope is very small, so y is changing very slowly in comparison to p. That's the rate of change. And just as a matter of nomenclature again, f prime of a is the velocity when f is the position function, and the speed is going to be the absolute value of the velocity. So the speed is always positive. The velocity is going to be either positive or negative depending on where you go. So this is an example with rates of change. I'll let you look at this on your own, but the idea is the same as before. The only difference is the interpretation that we have for this, which is to say how fast the function is changing near that given value that's given to us. This is all solved. You can look at it. But I'll stop here. I'll let you read this on your own. Rates of change, this is important. Thank you for keeping up with it up to this point.